our point 2 comma 6 on there. And when I type in 19x minus 32, and I hit graph, well, here it comes. And hopefully, the picture that you drew on your paper looks an awful lot like this straight line that we just calculated. And notice that for both of these functions, both the line and the curve function, when x is equal to 2, y equals 6, those two curves are, the curve is just being kissed by the tangent line that's moving along there, and it gets kissed right at 2 comma 6. All right, are there any questions about what we just did? There's a fair amount of algebra that went into that, but in the end, we were able to come up with the equation of that line that just kisses the curve.
So in the beginning, if it isn't 0 over 0, does that mean that we won't be able to get to a solution like this?
That's correct.
Okay.
And so in the end, if we don't have 0 over 0, we actually have a real issue. Because all of these problems, all of these slope problems, as long as your curve is smooth, meaning it doesn't have like a corner or something like that, as long as your curve is smooth, then this limit that we get for the slope of the secant line is describing a function that has just a hole in it. So we should always be able to do that. Okay, other questions or comments? Okay. Okay, so this was pretty cool, but there were some drawbacks in what we did. And one of the drawbacks that we have is that when factoring this thing up here, that was kind of a pain, right? And we had to use long division to do that. So there's an alternative idea that will actually make life a little bit easier and not require that we do long division. And so I'd like to share that idea with you. And Aaron, this is where the H version is going to come in. Okay, so an alternate idea for our definition of a derivative. So the alternate idea starts out exactly the same way. We have a function described by y equals f of x. And we are interested in finding the slope of a tangent line at an x value of a. And so what we'll do is we'll pick a second point on our curve, and we'll drop a plumb line straight down to the x-axis. Now, on our last way of setting this up, we just said that that point had an x value of just x. What we're going to do instead is we're going to say that second point is a distance of h away from our a value. Which means if I move a distance of h along the x-axis to the right of a, then this other x value over here is going to be a plus h. And so what that does for us is that it gives us 2 points. And those 2 points, we can draw a line between them. And the first point is the point A, comma, f of a. And that second point up there, the x value is a plus h. And the y value, well, I'm going to plug in that x value into my function. And so this is f of a plus h. And so now, if I write down the slope of this secant line, I've got f of a a plus h minus f of a over a plus h minus a. Now, my denominator up here, I can actually simplify this denominator up here. And I see an a, I see a minus a, so those guys cancel, and it really just leaves me with an h in the denominator. And so the slope of my secant line becomes f of a plus h minus f of a all over just an h. All right, so imagine that this board could move. I've got my fixed point a comma f of a. That point doesn't move at all. But my other point is sliding down the curve, and it's moving my secant line along with it until those 2 points are really close together. And so I'm allowing this a plus h x value to get close to my a value. Another way to say that is that I'm shrinking this distance of h. And so really, as I move my top point downward, I'm making h get really tiny. In other words, I'm taking a limit as h goes to 0. And so the slope of a tangent line to our function f at x equal to a is given by, well, we start out with our slope of our secant line, f of a plus h minus f of a, all over h, and we make that distance of h go all the way to 0. So I keep a fixed, and I shrink the right-hand side down. I'm taking a limit as h goes to 0. And so this is an alternate version of the derivative of a function at a. So f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. So this is our alternate idea. Okay, now at the beginning of class, when I wrote down the other version, the x minus a version of our derivative, I asked the person closest to this wall to say that definition out loud. Now I'd like the partner that is closest to this wall to tell your other neighbor about this limit definition of a derivative.
I don't understand.
Well, when you have an A minus an A, you get an H. Yeah, so if you do it that way, well, if you look at it, it's just going to cancel it out anyway. But you add to this and you subtract that.
Okay, please stop, even if you haven't finished saying it. Your time is up. All right. So there are now two limit definitions of a derivative. And you want to be comfortable with both of these versions. Okay? In other words, not for exam 1, but for exam 2, you want to be able to explain what the different parts of this formula mean. Okay, for example, we've got our h, that shows up down here. We've got our f of a plus h minus f of a, that's a distance along, that's our change in our y. And you want to be able to explain, and maybe explaining it to somebody in class after class, walk out and saying, hey, let's go get coffee, I want to tell you all about this limit definition of a derivative. And you can explain to them what the action is when we throw the limit as h goes to 0 into our secant line slope formula. Okay? So maybe find somebody in this class, and then they can humor you because they've already thought about it, or you can find somebody who's not in this class and teach them something about calculus. Okay, so let's take a look at an example using this particular version of our derivative.
Yeah, we could.
All right. So let's find the slope of a tangent line to the function f of x is equal to 3x squared minus 5x at the point 2, 2. Okay, so when I look at this, there's a few things going on. Unlike the last question that I asked, we're not trying to find the whole equation of a tangent line, we're just trying to find the slope. In other words, we are trying to figure out how steep this function is when x is equal to 2. Right, now, some things that you might want to do, you might want to graph this function, see what it looks like, and maybe sketch a picture of the tangent line and estimate its slope. That would be a fine thing to do, and then we can compare our answer and see if it's reasonable. Some other things you might want to do is you might want to verify that this is even a reasonable question, because we want to make sure that this point does in fact lie on our particular function. So does 2, 2 lie on f of x equals 3x squared minus 5x? And so we might check that by plugging in x equal to 2 everywhere I see an x. So we have 3 times 2 squared minus 5 times 2. So that's 12 minus 10, which does give us a y value of 2. So I haven't lied to you. Okay, so this point that we're talking about does in fact lie on our curve. Okay, so we'd like to figure out the slope of our tangent line. We want to answer the question of how steep is our function when our x value is 2. In other words, we'd like to find f prime of 2. So since I've just introduced you to this new version of our derivative, we're going to go ahead and use that one in this example. And so f prime of 2 will be equal to the limit as h goes to 0. On this version of our definition of a derivative, h always goes to 0. Unlike the other version, x went to a and you had to figure out what a was equal to. Here, we're shrinking that distance along the x-axis, so h will always go to 0. Limit as h goes to 0 of f of a plus h, so that's 2 plus h, minus f of a, so that's minus f of 2, all over h. So this is what we're setting up. Are there any questions about writing that part down? Okay, so now we've got some algebra to do and some work to do. So some things that we need to fill in. Well, f of 2, I look at my original function, f of x, and everywhere I see an x, I plug in a 2. Now, that's exactly what we just did here. So I could rewrite it over here, but we know now that f of 2 is equal to 2. And f of 2 plus h, well, this is where we trade off a little bit. Okay, with this new alternate version, we have a little bit more work to do right here. So f of 2 plus h says, I look at my original function, everywhere I see an x, I replace that x with a 2 plus h. Alright, so f of 2 plus h looks like 3 times 2 plus h squared minus 5 times 2 plus h. So this is work on the side, and we'll eventually fill it into our expression over here. All right, so what are some things we can do here to expand this out and start to eventually combine some terms if possible? Okay, what would you like to distribute?
3 and then 2.
This guy here? Okay, so we eventually want to distribute the 3, but before we can do that, we've got to square this guy out, okay, because of that power up there. So first thing we'll do is to expand out to 2 plus h times 2 plus h. So we've got 3 times 2 plus h times 2 plus h. Now this other part over here, we can distribute the 5. Okay, so we might as well go ahead and do that. So we've got minus 10 minus 5h. And so now I've got to work through 2 plus h times 2 plus h. So I've got 3 times 4 plus 2h plus 2h plus h squared. And I have minus 10 and minus 5h. We can combine these two h's into 4 h's. So we've got 3 times 4 plus 4h plus h squared, and then minus 10 minus 5h. And now we can distribute that 3. So we end up with 12 plus 12h plus 3h squared minus 10 minus 5h. All right. Can we do anything to clean that up a little bit? Okay, what kind of like terms?
You got 12h and you got negative 5h.
All right, so we've got a 12h and a negative 5h. So, all right, we've got a 3h squared plus 7h. Yeah, and then we've got a 10 and a 12, which gives us plus 2. So that whole thing simplifies down to 3h squared plus 7h plus 2. Okay. Any questions about that part? All right, so this is all of our side work. Let's go back over here. So now we're back to calculating our limit. We've got the limit as h goes to 0 of f of 2 plus h. Well, that's our work we just did over here. That's 3h squared plus 7h plus 2 minus f of 2. Well, f of 2 is 2. All over h. Now, since these parentheses are grouping things together before the subtraction sign, I don't really need them, so I can get rid of these parentheses. And so at this point, I have a limit that I'd like to solve. And so my very first thing that I might do is ask myself, if I plug in my limiting value, what happens? And in the denominator, we get a 0. And the same thing happens in the numerator. We've got a 0 plus a 0 plus 2 minus 2. So we end up with 0 over 0. So if we simplify, we should be able to do some canceling and some factoring. All right, so is there anything that we can do in that numerator?
We'll factor out the h in the numerator. Well, 2 and 2 is 0, and then 3h squared plus 7h becomes h times 3h times 7, or plus 7.
Yeah, so number 1, we can get rid of this 2 and the minus 2. Okay, and now we can factor some things out. And so we've got the limit as h goes to 0. And this is actually really good, because at this point, all we really need to be able to do is to factor out an h, to cancel it with the bottom. And so if we can factor out an h, we should be able to do a dance. Okay, we should be able to celebrate a little bit. And so this is good. We have a common term of h, and it leaves us with 3h plus 7 inside the parentheses, all over h. So if you're working with this particular limit definition of a derivative, and you're working through the problem, and you get to a point where you are not able to factor out an h in the numerator to cancel with the h in the denominator, something went wrong. Okay? So you want to go back and double check your algebra earlier on, because you should always, always, always be able to factor out that h in the numerator to cancel with the denominator.
Would there be a point where you'd get the 0, 0 and then wouldn't be able to, you got the 0, 0, shouldn't you be able to cancel?
We should be able to, that's right. So if we get to something that's not 0 over 0 here, then go back and recheck. Okay, so the h is canceled, and we are now left with the limit as h goes to 0 of 3h plus 7. No more denominator, life is good, and so we are now allowed to plug in our limiting h value. So everywhere I see an h, I can plug in 0, so we've got 3 times 0 plus 7. So final answer of 7. Okay, so what does that 7 tell us? That 7 is telling the slope of our tangent line. So it says our curve at the point 2, 2 has a slope of 7. Okay? And so if you wanted to draw a tangent line to this curve, your tangent line should have a slope of 7. And at this point, we've answered our entire question. We've got our 7 here, but if you were super excited about this particular problem and you wanted to do some bonus work on it, you were really excited and you've already graphed the function, then you might do the bonus work of writing down the equation of our tangent line. Our slope is 7, and our point is 2, 2. And so once we have that information, then we can write down that equation. We've got y minus y1. So y minus 2 is equal to slope times x minus x2. There's our equation of our tangent line. If I wanted to, I could simplify it. Y minus 2 is equal to 7x minus 14. Add 2 to both sides. And I have y is equal to 7x minus 12. So there's your bonus question. Equation of our tangent line is 7x minus 12. And so if you graph this line along with 3x squared minus 5x, you should see a curve and a straight line that just kisses this curve at 2, 2. Okay, are there any questions?